Hey, welcome back. It is time, finally, for Stokes Theorem. Let's do this. So I'm going to introduce Stokes Theorem in a similar pattern to how I talked about Green's Theorem. And really, you can think of Stokes Theorem as the three-dimensional version of Green's Theorem. Actually, it makes more sense to think of Green's Theorem as the two-dimensional version of Stokes Theorem. But anyways, here's the setup. If you have a curve C, and actually that curve has to be a closed loop, and everything that we're talking about here is in R3, so we have a closed loop in R3, and the second piece is a surface. It's a surface whose boundary curve is the curve C. And just like in Green's theorem, there's a piece about orientation. And I'll write it like this for now. I'm going to say that the two pieces are oriented what I'm going to call compatibly. I'll tell you what that means in a second, but here's a picture. And so again, the setup is that we have a curve that's the boundary of a surface. So here, this is like a sideways cup, and the rim of the cup is the boundary curve. And so the last piece we have is a vector field F, and that vector field has to be defined on the entirety of the surface. So if we have these three pieces and they satisfy these conditions, then the following equation holds. And it's an equality between two types of integrals. One of them is a flux integral through the surface S, and it's not of the vector field F, it's a flux integral of the curl of F. Remember that the curl of a vector field is a three-dimensional vector field itself, and so we're taking the flux of that through S. And Stokes' theorem says that that is equal to the line integral over the boundary curve C of F. So that's Stokes' theorem. Again, it looks a lot like Green's theorem, because on the right, we have a line integral over the boundary of an object. But now that object isn't a two-dimensional region in the plane. Instead, it's a surface in R3. And so the analogous operation to have on the left-hand side for this integral is a flux integral of the curl of the vector field through the surface. Now, since we have a line integral here and a flux integral here, these are both operations where we need to say what the orientation of the curve and the surface are. And when I'm talking about these two things being oriented compatibly, it's sort of saying that the orientations for them have to kind of have a specific interaction. So I'm going to tell you about that next. Okay, so here's the situation for the orientation. We have a surface, and remember that we orient surfaces by providing a normal direction. And we have a curve, and we orient curves by providing a direction around the curve. And those two orientations, we're going to call those orientations compatible if the following holds. So if you imagine you're walking on the surface S near the boundary, and your head is in the direction of the orientation of the surface, and also you're facing the direction of the orientation of the curve. So if you're standing on the surface in this way, then these two are oriented compatibly if it ends up that the surface is on your left. So this is kind of complicated, but the point of it is, if we have an orientation on one of these two things, we can use this to figure out an orientation on the other. So for an example, let's say that the orientation of the surface is outwards. So this is the unit normal vector for this surface S. Let's use this to figure out what the compatible orientation on the boundary curve should be. So I like to draw stick figures on my surfaces because I want to imagine myself walking on the surface. So it's saying if I'm walking on the surface with my head in the direction of the normal vector, and another way to interpret that phrase is that of the two sides of the surface to stand on, you're standing on the one so that the vector pointing in the direction of the orientation is also kind of pointing in the direction that's up for you. So we're standing here, and we want the surface to be on our left. So we want this to be our left hand, and that to be our right hand. Now, if you imagine that this is our left and this is our right, it means that the direction that we're facing is kind of away from the camera here. We're facing outwards that way. And what that means, since we're standing near the boundary curve, what that means is the boundary should be oriented this way, in the direction that we're facing. So that's how we can use the orientation of a surface to determine the orientation on the boundary curve. And again, it goes the other way too. In fact, for practice, here are two exercises for you. In the first one, you're given a surface with an oriented boundary, and you need to figure out an orientation on the surface, which will be either outwards or inwards. And in the second, you're given a surface with two boundary components, and the surface has an orientation. It's oriented outwards, away from the inside of this hourglass. And you need to figure out an orientation on both of these boundary curves separately. So this exercise is a great way to get used to what it means to orient a surface and a curve compatibly. So I highly recommend that you pause the video right now and try to work on this on your own. Okay, so for this first one, we need to figure out whether the right orientation for this is outwards or inwards. And you can just guess if you want and see how it works out. Let's suppose that we guess that the orientation on the surface should be outwards. Then I'll draw a little stick figure. We're going to pretend we're standing on the outside of the surface. And if we're walking in the direction of the orientation, it means we're walking this way. So we're kind of facing away from the camera here. What that means is that our left hand will be this one and our right hand will be this one. And now we can see that this isn't the right orientation because we wanted to be standing near the boundary so that the surface was on our left. Here, the surface is on our right. And so that sort of tells us off the bat that the correct orientation is inwards because this is not right. And now if you drew a stick figure that's kind of like walking on the inside here, if we're walking in the direction of the orientation, then this has to be our left hand and this has to be our right hand because in this picture, we're facing the camera. So there we go. So the correct orientation here is inwards. Now for this one, we want to orient the two curves. And this is sort of like the first example that we did earlier. We want to imagine we're standing near the boundary with our head in the direction of the normal vector. And we want to do that so that the surface is on our left. So we want this to be our left hand and this one to be our right hand. And if we do that, then in this picture, we're facing towards the camera. So this would be our face. And so if we're facing this way, it means we're walking this direction around the boundary. Now, if you do the same thing down here, you actually find that the orientation on this boundary curve is the other way. That's just sort of how it works out here. So that's how the orientation stuff works. Now, this is the equation for Stokes theorem. And I want to take a second to give you just a quick look into why it might make sense, like why these two things might be equal. The way I like to think about it is they're sort of measuring the same thing. And maybe the simplest place to see that is to imagine that the surface is a small disk. So here's our surface, S, it's this disk. Let's say it's oriented with a normal vector that's pointing up. And as we just saw, that means that the boundary orientation would have to be this way. So that if we're walking along the top of this disk in the direction of the orientation of the boundary curve, then the surface is on our left. So I haven't drawn the vector field here, but a way we can interpret the line integral, remember, is, well, a line integral, we think about it as how much the vector field is pointing in the direction tangent to the curve. If this curve is the boundary of this small disk, we can kind of think about it as it's measuring how much F is rotating around the boundary of the disk. In other words, this will be positive if the vector field is pointing around this axis here, parallel to the vector n, kind of counterclockwise. Or another way to think about it is as determined by the right-hand rule. Now, on the other hand, this flux integral of the curl, remember that we can interpret a flux integral as a scalar surface integral over the surface of the vector field that we're finding the flux of, which in this case is the curl, dotted with the unit normal vector. Now, remember that we've been thinking of the curl of a three-dimensional vector field as a vector that points in the direction of the axis of rotation of that vector field. But it turns out that there's another way we can interpret it, which is the curl of a vector field is a vector for which if we take the dot product of that with any unit vector, it will tell us how much that vector field is rotating around an axis parallel to this vector at each point in the domain of the vector field. So if we're thinking about that in this picture, what it means is that this number is going to be a measurement of how much the vector field is rotating around the axis parallel to this normal vector, again determined by the right-hand rule. So sort of if we're looking at this from above, it would be counterclockwise. So that's what this number represents. And now if this is a small disk, then taking a scalar surface integral of it will be more or less the same as just taking this number, this measurement of rotation, and multiplying it by the area of the disk. So that's meant to be a bit of an insight into why these are the same. The line integral is measuring rotation around the boundary, and the flux integral is almost doing the same thing. It's measuring how much the vector field is rotating around this axis. Now, that wasn't a proof, but hopefully this tells you a little bit about why we would expect this equation to hold. Now, the last thing for us to do is an example. Let's use Stokes' theorem to evaluate this line integral of the vector field negative yz, 5y, xy over a curve that is the circle of radius 3 in the plane y equals 2, and it's oriented counterclockwise when viewed from the origin. So the first thing we should do is draw a picture. So here's our circle of radius 3 in the plane y equals 2, and oriented counterclockwise when viewed from the origin means if we're standing here at the origin and looking at this circle, then it should be going counterclockwise. Well, okay, since in our picture the origin is sort of behind the circle, it means that from our point of view, the orientation will be clockwise. Okay, so let's write down what Stokes' theorem says here, because it turns out that we're not ready to use Stokes' theorem right away. Stokes' theorem is going to tell us that the line integral that we want to evaluate is equal to the flux integral through the surface S of the curl of f dot ds. Now, the issue here is that we haven't been given a surface S. So what we're going to do is actually, since we're not told what S is, we get to pick what it is. So we can pick any surface whose boundary curve is this green curve. And there's infinitely many of those. Probably the simplest one will be to let S be the disk that lies in this plane y equals 2. So it'll be the disk of radius 3 in the plane y equals 2. Now we need to figure out an orientation for this surface, and if we go back to that orientation rule, the correct side of the surface to walk on so that we're heading in the direction of the orientation of the curve and the surface is on our left, turns out that that's going to be the back side from our point of view. So the normal vector is pointing in the negative y direction. Okay, we're just about ready to use Stokes' theorem to evaluate this line integral. Before we do that, let's just compute the curl of f off to the side here, because that's what we're going to compute the flux of. To compute the curl, the first component, we take the derivative of the z component with respect to y, and the y component with respect to z. We get x. For the second, we take the derivative of the x component with respect to z minus the z component with respect to x, so we'll get negative 2y. And for the third component of the curl, we differentiate the y component with respect to x and the x component with respect to y, so we'll get a positive y. So this is our curl, and so what we get is that the integral that we want to evaluate using Stokes' theorem is equal to the flux through the surface of the vector field x negative 2y y dot ds. Now, you could parameterize this surface and compute the flux integral that way, but since our surface is a disk, it has a constant normal vector that always points in the negative y direction. So we can use the scalar surface integral interpretation of flux and evaluate instead the scalar surface integral of x negative 2y y dotted with the unit normal vector that points in that direction, which will be 0, negative 1, 0. Now, if we evaluate this dot product, we get a scalar surface integral of just 2y ds. And actually even more now, since our disk lies entirely in the plane y equals 2, our integrand is always going to be equal to 2 times 2. So this is equal to the scalar surface integral of 4 ds. And now we're good to go. We don't even need to parameterize the surface, because whenever we're doing a scalar surface integral of a constant, we just end up with that constant times the area of the surface. The surface is a disk of radius 3, so its area is going to be pi times the radius squared. And so the answer here, this line integral, which we got via Stokes' theorem, is equal to 36 pi. So that was using Stokes' theorem to evaluate a line integral. You'll see while working through worksheets and problem sets that we also use Stokes' theorem to evaluate flux integrals sometimes. But in those situations, we need to be careful because we need to make sure that the integrand is the curl of a vector field. You'll see what that means more as you're practicing. But that's how it goes. I'll note that we could have also evaluated this directly just by parameterizing this curve and evaluating it. I think for this particular example, it doesn't actually end up being that bad of a computation. But there are definitely situations where you have to compute a line integral of a particularly unpleasant vector field, and taking its curl makes it simpler. All right, so that's Stokes' theorem. There's a lot there to do with the orientation, and the fact that it's got a line integral and a flux integral involved means it's going to be complicated no matter what. Like everything else, it'll be something that will become a lot more clear as you practice. So good luck with that. Thanks for watching. We're almost at the end. So I'll see you in the next video.